All right, so let's get started. Today we'll look into a little bit deeper into AC analysis of MOSFETs, and also probably some of you might have questions on the exam problems and so on. We can try to cover some of those details as well. Okay. Um, all right. So what we had been looking into in the last lecture was this type of an amplifier where you had a MOSFET, you had the source connected to a resistance. And this, you already know that this is called a amplifier with source degeneration. Now, what type of amplifier is this? This is since you're applying your input at the gate and you're looking at your output at the drain, the common terminal would be the source terminal, right? So you have these three terminals: source, gate, and drain. So let's maybe write them down: source, gate, and drain. Now you can have your input at any of these three terminals. You can also have your output at any of these three terminals. The ones that are of interest to us is when you have your input at the gate and your output at the drain. So this is what we are looking at right now, even though the source terminal is not grounded, but this is kind of a common terminal because your VDS, the drain to source, is the output voltage in this case. And let's say the gate to source is the input voltage in this case. So this configuration is going to be called the common source configuration because your input is at the gate, your output is at the drain, and the source terminal can be considered as the common terminal. Now, of course, in this particular example, the source terminal was degenerated with this resistance, but there is always the possibility that, yeah, you do not have this resistance and this terminal is directly connected to ground. So in that case, it's easier to comprehend that why we are calling it a common source terminal, right? Because your source terminal is grounded and input is between gate and source, output is between drain and source. So that is going to be called a common source terminal. Similarly, you can have a common drain terminal and you can have a common gate or a common drain configuration and a common gate configuration, right? So there are three terminals. Any of them could be the common terminal. This is the common source. Today we'll look at the common gate as well as the common drain configurations. Okay. And in case of common drain, you'll see that the drain will be the common terminal. Your input will still be at the gate and your output will be at the source terminal. So, and in case of that's a common drain configuration. There is also a common gate configuration. In that case, your gate terminal would be the common terminal, and there we'll see that we'll apply your input at the source, and your output will be at the drain. So we'll take a look at these three different configurations in today's class. Common source is something that we have already started looking into, that your input is at the gate, output at the drain, and source is the common terminal. Common drain is where your drain will be the common terminal, input at the gate, output at the source. The example of that is basically the one of the problems that you have in your exam. So if I go back to your exam question, you see that there are two parts of this particular problem. That first you have a common source with source degeneration. So this is the common source. RG1 and RG2 are actually creating the bias. This is the source degeneration for biasing, but there is also a bypass capacitance that shorts this RS1 resistance to ground at AC frequencies or high enough frequencies. But there is also the second stage. There's also the second stage over here, which is the common drain configuration. Why are you calling it common drain? Because see, here the input is applied at the gate. So this is your gate terminal of the MOSFET. The output is taken from the source terminal of the MOSFET, right? This is the source terminal of the MOSFET, and the output is taken from the source. And that's why this is called a common drain configuration. This is also called a source follower. And we'll see that why do we call it a source follower configuration. So your exam question actually has both of these two configurations within the same problem. You have a common source and you have a common drain. Those are the two steps, but you can analyze the first stage and the second stage separately for solving the exam question. All right. But basically the crux of the concept is that there are three terminals in a MOSFET, and any of those three terminals can be the common terminal. So you can have a common source, you can have a common drain, or you can have a common gate. And the other two terminals, one of them will be the input, the other terminal will be the output. And you have also already looked into this common source with source degeneration, the common source with source degeneration, and you have found out that the effective GM is something that we are denoting with this uppercase GM here, and that is going to be lowercase GM divided by 1 plus GMRS, where lowercase GM is the transconductance of the MOSFET. But the transconductance of the entire circuit is given by the uppercase GM. And that is different, that can be different from the lowercase GM. And you also solved a problem in the last class where we had looked into this particular problem, which is very similar to your exam 2 problem, but just the first part. So again, let me go back. So this first part is actually what we just solved in the last lecture. It's exactly very similar to what you have here, that you have RG1 and RG2, that is for biasing. RD1 is the drain resistance, the load resistance, because the output is at the drain terminal for this, and the output goes to the input, which is the gate terminal for the next stage. And the output for the next stage, the second stage, is taken from the source terminal. Okay. So we'll take a look into those two different scenarios that, okay, we already looked into common source with source degeneration, and we have solved this type of a problem in the last lecture. Now, if I just recap a little bit, that first we wanted to find out what are the DC operating points, and then found the DC operating points. Then we wanted to find out the AC gain, and for that, we figured out what is going to be the uppercase GM, that is basically the overall transconductance of the circuit, that is GM divided by 1 plus GMRS, because the source is degenerated in this case. And that is same as your exam problem, just the numbers are probably different. And you found out what is going to be your uppercase GM. And the uppercase GM turned out to be about 0.34 milliampere per volt, whereas the lowercase GM was 8 milliampere per volt. And that is why we say that the GM has been degenerated. It has been reduced from the GM of the MOSFET. And then you found out what is going to be your equivalent RL, the equivalent load resistance at the output. What was the output terminal? The output terminal was this drain terminal. So looking into the drain terminal, the resistance that you see, looking up, you'll see RD. So looking here, looking up, you'll see RD, which is 5 kilo ohm. Looking down, you see the drain terminal of the MOSFET. And we'll prove this today, that looking into the drain terminal of the MOSFET, you'll see a resistance of RO. RO is the output resistance of the MOSFET. And RO is equal to 1 over lambda ID. That's something we had proved before. And now, because lambda is considered to be 0, if lambda is not given in the problem, we can consider lambda to be 0. That's basically saying that you have an infinite RO for that MOSFET. Or the ID VDS characteristic is exactly parallel to the x-axis for the MOSFET. So with that ideality in mind, of course, you do not see, you basically see an infinite resistance looking down at this point. Looking up, you see 5 kilo ohm. And of course, this RL is also connected at this particular terminal. So your equivalent resistance connected at this node, connected at the output node, is basically this RL in parallel with RD. And why are they parallel again? Because of course, one node is common. The other node is an AC ground. The top terminal of RD is connected to VDD, that's an AC ground. The bottom terminal of RL is connected to ground, which is also an AC ground. And that's why we say that they are in parallel to each other. So you have, oops, I think the screen is not visible. Let me go back to Zoom. So Zoom got disconnected for a moment. So I'm trying to share the screen once again. All right. So at the output terminal, you basically have your RD in parallel with RL. That's your equivalent resistance at this terminal, which is your output. and you solved this in the last lecture and found out that the equivalent output resistance is nothing but RD in parallel with RL, which gave you 4 kilo. Now the gain, if you consider that the input is at this particular terminal, which is the gate terminal of the MOSFET, the capital GM is converting the gate voltage which is present at the gate of the MOSFET to the equivalent output current which is flowing through the drain terminal of the MOSFET. So the job of GM is to relate the input voltage, which is the gate voltage in this case, to the output current, which is the drain current in this case. Right? That's the job of transconductance. It's a conductance quantity, which is the transfer function here. So if you multiply GM with the equivalent output resistance, you get the overall gain from the input terminal, which is the gate terminal of the MOSFET, to the output, which is the VO of the MOSFET. Right? And why GM times R out is an equivalent voltage gain quantity? Because GM, let's me write that down. GM times R out is, you can write GM as an AC change in the output current, so I out, divided by an AC change in the input voltage. Right? I out over V in, that's your GM. And your output resistance, output AC resistance, again, in this case, we are talking about AC resistances always. So I out times R out, that's nothing but your V out, right? So this you can write as V out over V in, and that is equal to your AC gain, output voltage divided by input voltage. And that's why we say that any kind of voltage gain will be of the form GM times R out. Okay. But the important thing here is that what you calculated here as GM times R equivalent is just the voltage gain from this point to the output node, the gate of the MOSFET to the output node. You did not consider anything which is connected on the left side of the gate of the MOSFET, right? And on the left side of the MOSFET, you just have a very simple voltage division because of the source resistance of the voltage source, and then this biasing resistances that were connected for the gate of the MOSFET. And that voltage division is something that you already found out in your homework 2, homework 3, all those problems. And you know that it's just a very simple voltage division of 240 divided by 240 plus 40, because this was 240 kilo ohms and this is 40 kilo ohms. So if you take into consideration that voltage division, you'll get the overall voltage gain from the input, which is over here, to the output, which is over here. And because the source is degenerated with the RS1 resistance, what you eventually have is a very small amount of gain, minus 1.14. So this is barely any kind of gain, because the gain of 1 means output is equal to input. This is 1.1. So that is barely higher than the input. And that is because your source has been degenerated. If the source had not been degenerated, which is basically what we are showing here, that if you consider a bypass capacitor, and again, this is something you have in your exam question, you have a bypass capacitor. And bypass capacitor means that there will be a short at the frequency of interest in parallel to this RS1. And if you have a short, then of course the overall capital GM that you had considered in the last problem, that which is lowercase gm divided by 1 plus gm RS, if your effective resistance becomes 0, then this gm RS becomes 0, right? Then your uppercase gm is nothing but your lowercase gm, which was a much larger quantity, 8 milliampere per volt. So if you have the bypass capacitance, the only difference is that your uppercase GM will now be equal to lowercase gm instead of lowercase gm divided by 1 plus gm RS. So in that case, you can recalculate your voltage gains once again. Your voltage gain from the gate of the MOSFET to the output node is going to be GM times R equivalent, which is 8 milliampere per volt multiplied with 4K. That's basically RD in parallel with RL. That is minus 32. The minus actually signifies that you have a 180-degree phase shift from your input to output, but the gain is 32, which is a pretty high number now. If you consider the voltage division at the input side, so basically your voltage division at the input side multiplied with this gain that you had calculated from the gate of the MOSFET to the output of the MOSFET, that gives you the overall gain, and then it reduces a little bit from 32, it reduces to 27.4, but that's still pretty high. So this is how you're going to solve the first part of your exam question. If you want to solve the, let's say, this AC analysis extra credit problem. The second part is a common drain or a source follower. And why is it a common drain? Because your input is at the gate, your output is at the source. So your drain becomes the common terminal in that case. So let's see how you're going to solve a common drain or a source follower problem. Something that resembles this particular exam problem. All right. So how do you analyze a common drain? So for a common drain, again, the easiest way to analyze any or the correct way to analyze any MOSFET-based problem is that you take the MOSFET and draw its small signal AC equivalent model. Now, you can have your small signal AC equivalent model as the simplest one, which is you just have a VGS, a gate to source voltage, and then an output current, which is GM times that VGS. And in this case, the GM is the GM of the MOSFET. So you have the lowercase GM. So GM times VGS is the ID current. So you just draw that simplest model of the MOSFET. If you want to make it a little bit more complex, you can consider RO. And in that case, RO will be in parallel with this. So it will look something like that if RO is considered. But if RO is not considered, which you should do because you are learning the MOSFET for the first time. So if you take the, for example, analog IC1 class, which is a graduate level class, there you may have to consider RO all the time because there the analysis is a little bit more complex. And then you need to take into consideration the RO. There are other non-idealities as well, something that emanates from a body bias voltage, which is again a non-ideality which did not talk about much. But those are the things that you consider in your analog IC1 class. But the basic idea remains same, that you have your MOSFET, you draw your AC small signal equivalent model for the MOSFET. Now, in this course, your AC small signal equivalent model is very simple. As you take more advanced courses, that small signal model becomes more and more complex. That's the only difference. But the analysis is still the same. No difference in that. Okay. Okay. So if you analyze this for the common drain configuration, so you apply your input at the gate, so over here, and you look at your output at the source. So in this case as well, you do not have much idea about what is going to be your source voltage because your gate voltage, your input is applied at the gate, but the source is not connected to ground. Source is, or basically rather source is connected to ground through a resistance. So the source voltage is a non-zero voltage. So your VGS is not going to be equal to your VG. Your VG or gate voltage is equal to your input voltage, but your VGS would be something that is different. The same analysis that you did for the common source configuration with a source regeneration. So GM times VGS is going to be the ID current. That's the current that is flowing through this path. And that same ID current will be flowing through RS1 because this is the current flowing through. And the same current is going to flow through RS1 because of KCL. The current has nowhere else to go. It has to flow through that resistance to ground. Okay. And again, of course, we have assumed RO to be infinite. In your graduate classes, the RO may not be considered to be infinite, or maybe even toward the end of this week's lecture, I'll show a glimpse of what may happen if you do not consider RO to be infinite. Of course, your analysis will become a little more complex, but the way you analyze will be exactly the same. All right. So if you do the same analysis that you did in the source degeneration case for common source, you'll find out your VGS is going to be VG divided by 1 plus GMRS. That's exactly the same equation that we learned in the last lecture. So your ID, which is GM times VGS, is going to be GM divided by 1 plus GMRS times VG. So of course, your effective GM in this case as well is GM divided by 1 plus GMRS. Right? So you still have source degeneration, and that makes sense because you do have a degeneration resistance at the source. So your effective GM is reduced to GM divided by 1 plus GMRS. All right. Now, what is going to be your V out? What is going to be your V out? The V out is going to be the current that is flowing at the output. You already found out what is the current that is flowing at the output. And in this case, remember that the output is the source terminal. That's the only difference from the previous scenario. In the previous case, the output was at the drain. Now, you're not considering the output at the drain, you're taking your output at the source, and that makes it a common drain configuration instead of a common source configuration. So you already found out what is going to be your ID. Your V out is going to be GM times VGS, right? The current that is flowing out of that source terminal multiplied with that RS resistance. So you can write down your GM times VGS times that RS resistance, and you can simplify it. The other way of thinking about it is that you already know the output current, you already know your output, or you already know your GM, which is going to be GM divided by 1 plus GM RS. Now you are interested in what is the R out, because you know that gain AV is going to be GM times R out. That's the same equation that we had used earlier as well. And we will keep on using this equation for the next few classes. So what is R out? R out is the output resistance looking at the output terminal. In this case, that is the source terminal. And again, just like the previous problem, looking at the source terminal, you see RS, that's the resistance looking down. And looking up, you see the source terminal of the MOSFET, right? So it will be the effective resistance of the source terminal of the MOSFET, which we don't know yet, right? We haven't calculated. We know that looking into the drain of the MOSFET, the resistance that you see is RO. Looking into the source terminal of the MOSFET, I'm just saying that you do not know that whether it's going to be the same resistance or not, right? So let's calculate what is the resistance that you'll see looking into the source terminal of the MOSFET. How can you do that? So if you calculate the Thevenin equivalent resistance for the source terminal of the MOSFET, you will find out what is the resistance looking into the source terminal. So it's again, the analysis method is something that you already know. I'm not teaching anything new here in today's class. The resistance looking into the source terminal of the MOSFET is the Thevenin equivalent resistance looking into any black box. You already know how to find out the Thevenin equivalent resistance looking into any black box. So you have your MOSFET, and instead of, so how do you analyze what is the resistance looking into the source? You put a test voltage source or a test current source at that particular node that you're interested in. So if you're putting a test voltage source, you find out the current, the voltage to current ratio will give you the resistance. If you're putting a test current source, you find out what is the voltage, and then again, voltage over current will give you the resistance. Same way that you found Thevenin equivalent resistance in any of your earlier classes or homeworks. And for doing that, of course, all the independent voltage or current sources need to be killed. So of course, if you have an input voltage source, which you had in this case, your input voltage source was connected at the gate, right? If I go back a little bit, so your input voltage source was connected at the gate. This is an independent voltage source. So to find out what is the effective output resistance, you just have to get rid of this independent voltage source. That means short the voltage source to ground. That's what you'll need to do. So your voltage source needs to be connected to ground, input voltage source. And at the output, you can connect either a voltage source or a current source and find out the other quantity, and the ratio of voltage to current will give you the resistance. Okay? Same as finding out any Thevenin equivalent resistances. So let's do that now. So this is your MOSFET with your gate terminal grounded, because you wanted to get rid of the input independent voltage source. The dependent current source remains, because in your Thevenin equivalent resistance, or when you find out Thevenin equivalent resistance, you just get rid of all the independent voltage or current sources, but you don't get rid of dependent voltage or current sources, right? So the GM VGS, that current will remain. Although your gate is connected to ground, so gate voltage will become zero. But the source voltage is a non-zero voltage, and that is the voltage that is developed if you are putting a IX current source over here at the top terminal of that IX current source. You'll develop a VX voltage, and VX over IX will give you the resistance looking into the source terminal. Question?
What happened to the RS one, the resistance at the...
So again, when you find out any Thevenin equivalent resistance, so let's say you want to find out the Thevenin equivalent resistance looking into this particular terminal, right? This is the black box. what are the first, and let's say there was an input voltage here, and there is a load resistance connected here, right? So this is again something that we had learned in the first few lectures of this course, and again in 3111. So what is the first thing that you do if you are trying to find out what is the resistance looking into this black box? Disconnect the load. You get rid of the load and you short this input voltage source. So what is the load connected in this case? The load was connected to RS, the source, right? So you get rid of, so if you're putting a voltage source, okay, let me go back here. So if you want to put a volt, so this is your output terminal, right? This is your output terminal. What is the load resistance that is connected to the output terminal? This is RS. So first thing you do is get rid of RS, make V input voltage connected to ground, and then find out what is the Thevenin equivalent resistance looking into the source. Because the Thevenin equivalent resistance looking into the source should not depend on any external resistance that you connect at the source. Right? Resistance looking into the source is the resistance looking into the source. It cannot depend on anything else that you connect at the source. So you get rid of whatever is connected at the source. Same as what you do whenever you try to find out the Thevenin equivalent resistance. All right. So the resistance looking into the source will be this Vx over Ix. Of course, your Vg is going to be 0, and you get rid of Rs while you are calculating this. Your Vg is equal to 0, and Vs is equal to your Vx. So the voltage Vx that gets developed across that Ix current source is basically the voltage at the source, right? So your Vs voltage is equal to Vx. So your Vgs is Vg minus Vs, that is 0 minus Vx, that is equal to minus Vx. Ix will be Gm times Vgs. Ix is basically the current that gets created at the drain terminal. So that is Gm times Vgs. And Gm times Vgs is going to be minus Gm times Vx, because Vgs is equal to minus Vx. So your Ix, you have found out your Ix as a function of Vx. So the resistance looking into the source, that is Vx divided by Ix, is going to be 1 over Gm. So see, this is now something interesting, that the resistance looking into the source of a MOSFET is 1 upon Gm. Similarly, if you wanted to find out the resistance looking into the drain of a MOSFET, so just the same analysis you could have done. Let's say I connect, this is my gate terminal, this is my source terminal. I connect my gate terminal to ground, and then you have this Gm times VGS. Okay, so that's the basic model of the transistor. So this is your drain terminal, this is the gate terminal, and this is the source terminal. If you want to find out the resistance looking into the drain terminal, of course, you'll get rid of the RD and you'll put a, let's say, a source, a voltage, a test voltage or a test current source here. But in that case, because your gate is connected to, let's say, ground, and let's say your source is also connected to ground. So this is the common source configuration, for example. And if you're trying to find out what is the resistance looking into the drain terminal, of course, Gm times VGS is going to be 0 as well, because gate is 0, source is 0. So VGS is 0, Gm times VGS is going to be 0. So whatever test voltage source you connect, your test current coming out of that voltage source is going to be 0. So if voltage is finite quantity, current is 0, voltage over current, which is your resistance, is going to be infinity, right? That's why we said that resistance looking into the drain of the transistor is infinite if your RO is infinite. If your RO is finite, you basically have a parallel RO. So you have this RO, which is in parallel to Gm VGS. But of course, because VGS is equal to 0, Gm times VGS is also 0. So there's no effect of this Gm times VGS at all, right? So Gm times VGS, it's as good as it's not present at all. So in that case, the resistance that you see looking here is basically your RO. And that's why we said that looking into the drain of a transistor, you see RO, and looking into the source of the transistor, you see 1 upon GM. There is only one scenario or only one exception of this rule. We'll talk about that as well. But in general, the resistance looking into into the source is 1 upon GM. Resistance looking into the drain is RO. And that is the reason why sometimes people will say, I mean, if you go to an interview in TI, they might ask that what is the low resistance terminal and what is the high resistance terminal. So generally for a transistor or a MOSFET, the source is always called the low resistance terminal or the low impedance node. And drain is always called the high impedance node. Again, why? Because source is 1 upon GM, and you can calculate, like the GM will be given in the problem, or you can calculate GM. You'll see 1 upon GM is generally comes out to be a low number, a small number. Of course, much smaller than your RO. RO is output resistance, and ideally output resistance should be infinitely large. So looking at the drain terminal, you'll see a larger resistance. Looking at the source terminal, you'll see a smaller resistance. And that is the reason why people call the source terminal as a low impedance node and the drain terminal as the high impedance node for a MOSFET. So if you go to an interview in TI or analog devices, people might ask about what is the low impedance node in this circuit. So don't get confused. They're basically talking about the source terminal of the MOSFET in question, if they're talking about the low impedance node. And the high impedance node will be the drain terminal. Of course, the gate is also the high impedance node because gate has an insulator and it has infinite impedance because of that. Question?
Say like resistance looking into
yeah.
So for instance, if we have like 1 ohm resistance looking into the source node, is it equivalent to like seeing a resistor connected to ground? Like when we say resistance looking into a node, it's always relative to like AC ground?
Yes. Yes. So again, think about that black box. That okay, if you're looking into this particular node, you're always referencing it with respect to this, which is often grounded, right? So you're talking about the resistance looking into the source node with respect to the AC ground in this case. Okay, so that's correct. All right. So resistance looking into the source is 1 upon GM. That's a very interesting and very important conclusion. Okay. Now, what does that mean? So again, let us go back to the circuit once again. That if you try to find out the resistance looking into the output terminal, which is this, you see one path which is here, resistance looking into the source, and the other path is here, resistance looking down, which is RS. So looking up, you have 1 upon GM. Looking down, you have RS1. And basically, both of them are referenced with respect to AC ground. So they are both in parallel. So 1 upon GM in parallel with RS1, that's your output resistance for this circuit. So your output resistance for this circuit is 1 upon GM in parallel with RS. Of course, what does that mean? That if your GMRS, so this is equal to, so let me write that down. This is equal to RS1 divided by GM. And then 1 plus GMRS1 divided by GM. Right? So if I just calculate that, what is my 1 upon GM in parallel with RS1? So A parallel with B is A times B divided by A plus B. That's all I did here. So of course, this 1 upon GM will go away. So we have RS divided by 1 plus GMRS. So if GMRS1 is much, much larger than 1, if GMRS is much, much larger than 1, so of course, 1 plus GMRS will be almost equal to GMRS. In the numerator, you have RS1. So your R out is going to be almost equal to 1 over GM. So that is another way of saying is that if your RS, if the RS resistance is very, very high, and in that case, your GM times RS will be much, much higher than 1, then your R out will be almost equal to 1 over GM. And again, this is just the two parallel resistors, that if you have two parallel resistors, one of them is very small as compared to the other, then the overall parallel resistance will be the smaller resistance. So looking up, you have 1 over GM1. If 1 upon GM1 is much smaller than RS1, then of course the effective resistance looking into this terminal will be equal to 1 over GM1, right? So, and that's the same as saying GM-RS1 much larger than 1, or 1 over GM is much smaller than RS1. So just two resistances, whichever is smaller, if it is much smaller than the other, the overall resistance will be equal to the smaller resistance, right? That's all we are saying. All right. So now if we go back to your exam problem, your second stage is this one. And your effective GM for the second stage is going to be GM2. That's basically the GM of the second transistor divided by 1 plus GM2 times RS2. That's the effective GM because of the source degeneration. If what is the effective R out? Effective R out is the R out looking here. That's going to be, so R out, let me write that down, equal to 1 over GM2 in parallel with RS2. And in this case, you can actually calculate the exact value as well. But if 1 over GM2 is much smaller than RS2, this will be almost equal to 1 over GM2. Okay. Yes.
The resistance always infinity because there's no current.
Ideally, yes, but there could be leakage. Even through an insulator, there could be leakage currents. So there would be a very high resistance, but ideally it's always infinity. You can consider it to be infinity. Practically, it may not be infinity. We'll also look at one problem like that later. All right. So you can find out your R out. You can find out your GM. Multiply the two, you'll get your gain for the second stage. And you'll see that the gain for the second stage is almost equal to 1. Right? So let's see why is this almost going to be equal to 1. So basically, what you can write down is your let me write it down here. So your GM is equal to GM divided by 1 plus GMRS. And your R out is almost equal to 1 over 1 upon GM. But if you calculate so basically 1 over GM in parallel with RS1, so that's something we already calculated. So that was RS1 divided by GM. And in a new denominator, you will have 1 plus GMRS1 divided by GM. So again, just A in parallel with B is A times B divided by A plus B. That's what we did. And then let's say this GM and this GM will cancel out. So your R out is RS divided by 1 plus GMRS. And you can calculate your capital GM as GM divided by 1 plus GMRS. Now, if you multiply the two, of course, the 1 plus GMRS will get cancelled. But if your GM and RS are very close to each other, or GM times RS, you'll see in the particular problem that has been given, you'll see that the overall multiplication will become almost equal to 1. The other way of thinking about it is that your output voltage is going to be the output current multiplied with the resistance that you have here. And if you multiply those two, in that case as well, you'll see that your GM divided by 1 plus GMRS times RS1 times VGS. That's going to be your output voltage. And GMRS divided by 1 plus GMRS, if your GMRS is much larger than 1, you'll see that this voltage gain will be almost equal to 1. And it will always be little bit less than 1, but it will always be almost equal to 1. So that is a property of the source follower or the common drain configuration, that your overall voltage gain is going to be almost equal to 1 all the time. So why do we use this kind of a circuit then? If the gain is always equal to 1, and if it is, so we know that the job of an amplifier is to amplify the voltage. In this case, you are not amplifying the voltage. The maximum you can have is a voltage gain of 1, because your numerator is GM times RS1, your denominator is 1 plus GM times RS1. So if your GM times RS1 is much larger than 1, in that case, your overall voltage gain will be almost equal to 1, but never more than 1. So this is an amplifier which can have a maximum gain of 1. So why do we use a source follower in that case, or a common drain amplifier? We'll come to the fact that why is it called a source follower. But why do we use this kind of an amplifier? That is because this input of the amplifier, which in this case it is assumed to come from a voltage source over here, right? VI, this input voltage source. If the voltage source does not have enough driving capability to drive a resistance of RS1, what do we mean by that? Let's say this voltage source had a series resistance connected with it, which is, I don't know, let's say 1 mega ohm. And let's say my RS1 is equal to 1 kilo ohm. So the series voltage source, or this VI input voltage source, is a very bad voltage source for some reason. And what can be a bad voltage source? Again, in this case, we are assuming that the input voltage source is ideal, but it can be generated by another MOSFET-based circuit, right? And it's always possible that the output resistance of that MOSFET-based circuit is not very low. Ideally, any voltage source should have a zero output resistance. But MOSFET does not have a zero output resistance. MOSFET has infinite output resistance. We know that, right? So if you're using a MOSFET-based circuit, it is possible that your output resistance is high, even though you're trying to use that as a voltage source, right? In that case, that 1 mega ohm resistance, if you directly had connected this RS1 over here, so let's say your circuit looked like this, that this is the input voltage source with 1 mega ohm resistance, and then you had a load resistance of 1 kilo ohm. The voltage that you develop across this 1 kilo ohm resistance will be very, very small, because there will be a huge amount of voltage division between the two, and across the 1 kilo ohm, you'll have a very, very small amount of voltage, right? So this will not serve even if you're generating the voltage here, you will not get your voltage across the load resistance. And that is what we say, that is the scenario when we say that the driving capability of the voltage source is bad. It cannot drive the 1 kilo ohm resistance, because the input voltage source itself had an output resistance of, let's say, a mega ohm. And that is always possible because that input voltage source could be created using MOSFET-based circuits, and MOSFET-based circuits can have a higher output resistance. So it is quite possible that you will have a high output resistance for the voltage source, whereas the load is low. Okay? So if you want to avoid the effect of that voltage division, what you can do is that use this common drain configuration. Because looking into the gate, you will always see infinite resistance. The 1 mega ohm resistance of the voltage source does not matter. There is no voltage division here. But you are able to get a gain of 1, which means whatever voltage you are generating here with a very bad driving capability, you see the same voltage at this point with a good driving capability. Okay. So common drain is used as a buffer. So you have heard about, like, for example, amplifiers or op amps can be used as a buffer, right? So your gain will be equal to 1, but you'll have better driving capability. Buffer or a driver has better driving capability. So that is the use of this common drain configuration in any amplifier-based circuit. And that's why in the exam question, your second stage is this common drain, not your first stage. First stage gives you the gain, but let's say the first stage, the output of the first stage, you might calculate this as well, that the output of the first stage, which is here, looking here, you will see a large resistance. It will be RD1 in parallel with whatever you see looking down, which is RO in this case. That's a large number. But you can calculate your RD1 and then you can see whether this RD1 is sufficient to drive RL or not. And if it is not sufficient to drive, maybe it's a good idea to use a common drain configuration to drive that final load resistance. So that is why you'll be using the common drain configuration in any circuit. Why is this called a source follower? This is called a source follower because the output is taken at the source and the source voltage follows the gate voltage, which is the input. The input is at the gate. Whatever voltage you provide at the gate, the output, which is at the source, follows that input voltage. And that's why it is called a source follower. And that also gives you the impression that the gain of this circuit will be equal to 1 because it's a follower, it's not an amplifier. All right. And finally, the other configuration that you can think of is basically common gate. For a common gate, your gate will be the common terminal. Your input is applied at the source. So this is where your input is applied, or basically your input is, let me clear this up. So this is a biasing current and your input voltage is here, which is AC coupled at the source terminal. So your input is applied at the source terminal. Your output is taken from the drain terminal. And your gate terminal is the common terminal over here. In this case, the interesting thing is, again, looking into the source terminal, you'll see a 1 upon GM resistance, which is a small resistance. Your 1 upon GM will be a small resistance, and that's what you'll see looking into the source terminal. And because of that reason, this is less useful as a voltage amplifier. Why? Because you have a voltage source over here, and then you're applying that voltage source to a very low resistance. Generally, that's not a good idea, right? Because if you have a voltage source, you have some series resistance to it, and then if you connect a load resistance over here, which is small, if your load resistance is small, then you'll definitely see a voltage division. If your load resistance is very large, ideally, if it is open, then you'll not see any kind of voltage division for a voltage amplifier or a voltage-based analysis. So this is not a good idea to have a voltage input connected to the source terminal. We'll still try to, but if this voltage source is ideal, then there's no problem. Because if this voltage source is ideal, this resistance is 0. And if this resistance is 0, there is no voltage division, then it's okay. On the other hand, if you have a current input, you should apply the current input to a low impedance node, right? Because again, voltage and currents are duals of each other. We know that the voltage source should ideally have a 0 output resistance. On the other hand, current source ideally should have an infinite output resistance. And if the load resistance is a small resistance, then the entire current will go into that load resistance. So let me draw that scenario as well. Let's say you have a current source and you have an infinite output resistance of the current source. And then you have an RL. So ideally, if the output resistance of the current source is infinite, then all the current will go to RL. Right? There will be no current flowing through RO, but all the current will go through RL. So, but that's the ideal scenario. Of course, current sources are not ideal. So your RO will not be infinite. And in that case, there is a chance that there would be a division of currents between RO and RL. However, if RL is small, then you can expect most of the current to go through RL because current always takes the path of least resistance. So for a current source, it's better to connect the current source to a low impedance node, then all the current will go through that low impedance node. But for a voltage source, it's always better to connect the voltage source to a high impedance node. And that's why in the previous two scenarios, our input was connected at the gate, which is the highest impedance node for a MOSFET. So your input impedance is small. What would be the gain? You can calculate the gain by the same method that we had applied before. But the easiest way to calculate or understand or remember what is going to be the gain for the common gate is that the basic difference between common gate and common source is that for common source, your input is applied at the gate and your source terminal is grounded. For common gate, your input is applied at the source and the gate terminal is grounded. So your VGS for common gate is exactly equal to the VGS of common source, but it's negative, isn't it? Because your input is applied at the source instead of being applied at the gate. So VGS, which is VG minus VS, VGS for the common gate will be minus of VGS for the common source. And that's the only difference that you have in terms of calculating the overall voltage gain of the common gate. You can do that analysis that we had done earlier, but overall you'll see that you'll find the same gain, which is GM times RL equivalent. But in this case, it will be plus because your VGS is calculated in the opposite direction for this particular configuration, right? So you have that additional minus sign, and that's why your gain will be positive, which means that there is no 180-degree phase shift in this case. But with common source, you have a 180-degree phase shift. With common gate, you do not have the 180-degree phase shift, but the value of the gain is same, assuming that you can have an ideal voltage source over here. But of course, if you don't have an ideal voltage source, there will be a voltage division between the non-ideal voltage source resistance and the load resistance of the source terminal, which is 1 upon GM. But otherwise, if you have a ideal voltage source, you're going to have plus GM times R equivalent. So you have a 180-degree phase shift if you have a common source configuration, but you don't have that 180-degree phase shift if you have a common gate. Also for common drain, you do not have that 180-degree phase shift because again, you can find that out from the small signal model as well. But the easiest way to understand that is the current that is flowing through the drain terminal, the same current flows out of the source terminal. So the voltage that you developed at the top terminal of the RS is in the same direction of the current flow, right? And that is why there is no 180-degree phase shift between the input voltage source and the output voltage for the common drain. So only the common source has a 180-degree voltage difference between the input and output. The other two configurations do not. So let's stop here. In the next lecture, we'll look at a few examples.